From a previous video, we learned that the area of the triangle ABC, which we'll call K, can be written by this really nice formula, which is the semiperimeter, or the radius of the eccentre, which we call RC in this case because it's opposite the C, times the semiperimeter minus C. So the same thing's true at A and B, where you get the radius minus the radius of the x circle opposite A times S minus A, and radius of B, S minus B. And so if you use this formula and you compare it to Heron's formula, which is a very natural thing to do in this problem because that S minus C looks very similar to Heron's formula. And Heron's formula says the area of a triangle can be found by multiplying together the semiperimeter times the semiperimeter minus each of the sides, and then you take the square root of it. And if you square both sides, you end up getting that the SC squared equals, well, if you square both sides and this goes away and you get an S minus C squared, right? And so you're going to get S times S minus A, S minus B, and S minus C divided by S minus C squared. But we've got one S minus C in the numerator, and so we're going to cancel that out and just be left with the radius squared is equal to S times S minus A times S minus B over S minus C. Well, if C is this length right here, and so the larger C is, for instance, if C was the largest side, then S minus C would be very small. And so if you imagine this, right, the semiperimeter is always going to be the same, and then you got this S minus A, S minus B, and S minus C, and the smallest one is going to be what you, when you divide by the smallest one, which would be S minus C if C was the longest side, then you're going to divide by a smaller number, and you divide by a smaller number, you get a bigger result. So from this result right here, we can see that the RC, compared to the other X circles, is going to be dependent upon the size of C. The bigger C is, the bigger RC is. And then from that result, we get this theorem right here. We can kind of do the same idea, not that same result, but if we look at Heron's again, we get this, right? But because of this result, we can write each of the S minus C as K over RC, and you could do that for all three of them, including the radius of the inscribed circle, which would be S equals K over R, where R is the radius of the inscribed circle, because the area of the triangle can be written as the inscribed radius times the semiperimeter, or the end radius times the semiperimeter. So because of that, if we plug all these in, we get this nice result where we get K over R, K over RA, K over RB, and K over RC, which gives us K equals, well, the numerator is going to be K to the fourth, and the denominator is just going to be the product of all four radii, the three Exradii, and then the end radius. We could take the square root and get, that's going to equal K squared over the square root of that denominator. And then if we just switch places on that K and that square root, we end up with this formula, which is K equals the square root of R times RA times RB times RC. And that is a very nice result and a very nice connection between all of these X radius and the N radius and the area of the triangle.